Swayam Prabha. Digital India. Educated India.
Well, good morning everyone. So, we will be starting whatever we have done left in the last class. We were discussing about the properties of the vectors, and in the last class we have seen what is called the independent set of vectors, dependent set of vectors, definition of space. So, we start from that point onwards in this class. The dimension of the space is basically if there are n number of independent vectors present in the vectors or function that is present in the space, then every n plus 1th vector or function can be expressed as a linear combination of all these independent vectors. So, then the dimension of this space is called, it is n dimensional space. For example, if we have a 3 dimensional space, then we can there will be existing 3 vectors which are independent, and any 4th vector will be dependent, and it can be expressed as a linear combination of all these 3 independent vectors. Now, in this class we will just first look into one example, that let us consider an R3 space. It is basically a 3 dimensional space where the vectors 1 0 0, E2 0 1 0 and E3 is 0 0 1. This set of vectors, 3 vectors, will constitute an independent set of vectors. So, they constitute an independent set of vectors. So, alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3 is equal to 0 if and only if the coefficients alpha 1, alpha 2 and alpha 3 all are identically equal to 0. So, therefore, these 3 vectors are called the independent vectors. Any other vector, any 4th vector in the space, any other vector can be expressed a linear combination of these 3 vectors E1, E2 and E3. 4th vector can be expressed as a linear combination of independent set of vectors. So, for example, if we talk about a 4th vector E4 as 2 7 29 anything, then E4 can be expressed as a linear combination of these 3 vectors 2 E1 plus 7 E2 plus 29 E3. So, any set constituting the vectors E4, E5 or up to En, okay, they will constitute a dependent set of vectors. Okay. So, next we talk about something called basis of vector or basis set. It is very important, basis set of vectors. This is a set of independent vectors in the space we are considering. So, therefore, the the constituent of the basis set vectors are all independent vectors. So, any other vector in that space can be expressed as a linear combination of basis set vectors. Okay. So, that is very important. Any other vector belonging to the space can be expressed as a linear combination of basis set vectors. Then we talk about some of the important properties called orthogonality of the vectors. Two vectors are termed as orthogonal if they are perpendicular to each other. That means, the orientation, the angle between the two vectors is 90 degree. So, two vectors are termed as orthogonal if the angle between them is 90 degree. In other words, if you look into the property of the vector, which will be responsible to indicate the orientation of the two vector is the inner product. So, this has a direct implication of the inner product of the two vectors, because inner product indicates the orientation of vectors, and if you remember, the inner product is nothing but the dot product of the two vectors. So, it will be the dot product of two vectors is nothing but the magnitude of the two individual product of the magnitude of the individual vectors multiplied by the cosine theta, where theta is the angle between them. So, if the angle is 90 degree, then cosine 90 is 0. So, therefore, the inner product will be turning out to be 0. That means, if inner product between two vectors u and v is equal to 0, then u and v are mutually orthogonal. Therefore, this equation gives a criteria of orthogonality of the vector. Now, what is the orthonormal set? So, what is the orthogonal set of vectors? The orthogonal set is a set of vector that a set of vectors where these vectors are mutually orthogonal. That means, this is a set, this set is constituted by u1, u2, ui, uj, like that. So, for any two vectors, the inner product of the two vectors will be equal to 0, then this set of vectors is called mutually, they will be they constitute a set of orthogonal, they constitute orthogonal set. Then next one is orthonormal set. Again, in this case, this is a set of orthogonal vectors where norm of each vector is unity. That means, we are talking about of the set, the earlier set, maybe a different set S prime, which one is nothing but u1 prime, u2 prime, ui prime, uj prime, like that. So, u1 prime is nothing but u1 divided by norm of u1. So, we make sure that the norm of this vector will be unity. So, any arbitrary vector will be nothing but ui divided by norm of ui, and of course, they will be orthogonal to each other, because these vectors are orthogonal to each other. So, inner product between ui prime and uj prime will be always equal to 0. So, the basic criteria to of the vectors which will be forming the orthonormal set is that they will be mutually orthogonal to each other, as well as their norm will be equal to 1. So, that particular set is termed as orthonormal set. So, what is the corollary? The corollary is that any vector in the space where we are working can easily be determined by the orthogonal basis set. Okay. So, if we have any unknown vector in the space, that can be expressed as a linear combination of all these independent set of vectors, which are basically the constituents of the basis set, and if these vectors are orthogonal to each other, then you will be getting advantage of some of the properties, and the whole calculation has been enormously simplified. We will just look into this. So, let us try to prove this corollary or the interpretation. The proof goes like this: we consider u1, u2 and u3 is a set of orthogonal vectors, basis set vectors in R3 space. Okay. And so, it is a 3-dimensional space, and we can identify that u1, u2, u3, they are basically mutually independent to each other. Now, we have y, an arbitrary vector arbitrary fourth vector in same R3 space, then these vector as the definition of the independent vectors, it will be dependent and it can be expressed as a linear combination of all the in terms of the basis set vectors. That means, y can be expressed as beta I ui, where the index I runs from 1 to 3. So, these will be beta 1 u1 plus beta 2 u2 plus beta 3 u3, and these beta i's are nothing but the scalar multiplier, as these are the linear combination. So, if that is the case, then our aim is to evaluate what are these individual multiplier, so that any vector in the space can be expressed as a linear combination of the basis set vectors. So, next is that our aim is that beta I to be determined. How this will be determined? If suppose this is equation number 1, if we take inner product of this equation 1 with respect to u1, let us see what we get. So, we take inner product of equation 1 with respect to u1, let us see what we get. So, this is the inner product of u1 is equal to inner product of beta 1 u1 plus inner product of beta 2 u2 u1 plus inner product of beta 3 u3 u1. Okay. So, let us try to simplify this equation. So, inner product of y and u1 will be nothing but we invoke the property of the inner product, that inner product of alpha x y is nothing but alpha inner product of x and y, where x and y are the two vectors and alpha is the scalar multiplier. So, therefore, beta 1 can be taken out and it will be inner product of u1 and u1 plus beta 2 inner product of u2 and u1 plus beta 3 inner product of u3 and u1. Now, since u vector is a set of orthogonal basis set vector, therefore, u inner product of u2 and u1 will be equal to 0 by definition, because they are mutually orthogonal to each other. Inner product of u3 and u1 will be equal to 0. On the other hand, if you look into this, we can identify in the whatever we have studied in the last class, that inner product of u1 and u1 is nothing but the norm of u1. So, therefore, this equation boils down to inner product of y and u1 is nothing but beta 1 norm of u1 square. So, beta 1 can be identified as the following quantity: inner product of u and y and u1 divided by norm of u1 square. Similarly, we can identify what is beta 2. This is nothing but inner product of y and u2 and norm of u2 square, and beta 3 is nothing but inner product of y and u1 divided by norm of u3 square. So, if the we have considered the basis set is constituted by the orthogonal vectors u1, u2, u3. Now, if we would have made the basis set is constituted by orthogonal orthonormal vectors u1, u2, u3, then all these norms would have been equal to 1. So, that simplifies the whole lot of things. If basis set is made by orthogonal orthonormal vectors, then it has two simultaneous properties, that in this set the individual vectors are orthogonal as well as their norm is equal to 1. That means, u1 square is equal to norm of u2 is equal to norm of u3 square equal to 1. So, in that case, the denominators of all these scalar multipliers will be equal to 1, and the whole thing has been tremendously simplified, and you will be getting beta 1 is equal to inner product of y and u1, beta 2 is nothing but inner product of y and u2, and beta 3 is equal to nothing but inner product of y by u3. If you have n dimensional space, then let us say un for n dimension, this for 3 dimensional one, for n dimensional space we can generalize this one, that un is constituted by n number of basis set vectors which are mutually orthogonal and orthonormal. So, therefore, any ith vector or any nth vector, the coefficients beta n will be expressed as the inner product of y and un. That means, if y is a vector that can be in that space, in the n dimensional space, apart from the basis set vectors, it can be expressed as a linear combination of all the independent all the basis set vectors, and the corresponding coefficient can be evaluated by taking simply the inner product of the other vector and the nth vector of the basis set. So, in this way we can identify, we can express the vectors in terms of linear combination of the basis set vectors. So, for that, suppose you will be having a basis set vectors which will be, but it does not ensure that you will be getting a orthonormal and orthogonal set of vectors. So, there is a definite method available to convert all the basis set vectors into mutually orthogonal and orthonormal vectors, but before looking into that particular method and technique is known as the Gram-Schmidt orthogonalization technique. But before going into that, we just look into some of the examples to illustrate the properties of the vectors that whatever we have learned till now. So, first example that goes is that suppose there are 3 vectors is given 2, 1, 3. Let us say u1 is 2, 1, 3, u2 is 4, 1, 5 and u3 is 2, 0, 2. Now, the point is, question is that whether ui are dependent or independent. Okay. So, for that, if you consider the equation summation of C I u I is equal to 0, then we can obtain these following equations. So, that means C 1 2 1 3 plus C 2 4 1 5 plus C 3 2 0 2 is equal to 0. So, let us consider this equation where the coefficients C 1, C 2, C 3 are all scalar multiplier. So, you will be constituting 3 equations out of this. 2 C 1 plus 4 C 2 plus 2 C 3 is equal to 0. Then C 1 plus C 2 plus C 3 multiplied by 0 is equal to 0, and 3 C 1 plus 5 C 2 plus 2 C 3 is equal to 0. So, this is the first equation, this is equation number 2, this is equation number 3. Then let us try to find out what are the so 3 equations, 3 unknown. Let us try to find out what are the values of these scalar multipliers C's. So, from equation 2 we will be getting C 1 is equal to minus C 2, and from 1 and 2, if that is the case, by combining these two we can get we just put C 1 is equal to minus C 2. So, it will be minus 2 C 2. So, it will be 2 C 2 plus 2 C 3 is equal to 0. This is equation. So, you just simplify it further. So, it will be divided by 2. So, it will be C 2 plus C 3 equal to 0. This is equation number 4. Similarly, from equations 2 and 3, what we get is that you express C 1 everything in terms of C 2, substitute C 1. So, it will be minus 3 C 2. So, it will be 2 C 2 plus 2 C 3 will be equal to 0. So, C 2 plus C 3 equal to 0. So, this is equation number 5. So, if you look into now you will be having 2 equations and 2 unknowns, but the point is if you look into this equation 4 and 5, they are identical and they represent an identity. Now, the solution is C 2 is equal to minus C 3, and there will be infinite number of solutions can be present in this system. There will be no definite unique answer. So, infinite number of solutions are possible, and therefore, this set of vectors are dependent set of vectors, they are no longer independent set of vectors. So, ui constitute a conclusion is ui constitute a dependent set of vectors. There is another test to check whether the set of vectors are dependent or independent. That test is that we evaluate the determinant produced by these three equations. Basically, the elements, the coefficients of these three equations will be the elements of this determinant. So, if this determinant will be 2, 1, 3, 4, 1, 5, 2, 0, 2. Now, if you would like to find out what is the value of this determinant, just open up this determinant 2. So, it is 1, 5, 0, 2 minus 4, it is 1, 3, 0, 2 plus 2, 1, 3 and 1, 5. So, this becomes 2 multiplied by 2 minus 0, the cross multiplication minus 4, 2 minus 0 plus 2, 5 into 1 minus 3 into 1. So, therefore, this will be 4 minus 8 plus 2 into 2 4. So, therefore, this will be 8 minus 8 equal to 0. So, therefore, this determinant is equal to 0. If the determinant is equal to 0, then there will be infinite number of solutions present into the set of equations involving the coefficients C1, C2 and C3. So, this indicates that the basis set vectors, the vectors that we are talking about, they constitute a dependent set of vectors. That is a quick way of evaluating the to determine the whether the vectors are dependent or independent. So, by this method we can evaluate the, let us try to summarize whatever we have done. If determinant, the determinants are basically constituted by the elements of vectors, okay, if determinant is constituted by the elements of vector. Now, if determinant is not equal to 0, then vectors constitute independent set. If determinant is equal to 0, then this set of vectors are dependent set of vectors. So, given a problem, we can identify the determinant of the constituted by the corresponding coefficients of the elements of the vector, and we can go about it. Next example is again for the R3 space. These are U1 is 2, 1, 3 transpose, U2 is 4, 1, 5 transpose, and U3 is 2, 0, 4 transpose, then we just change the some of the elements, the last element of the last example, and we have to check whether they constitute independent or dependent set of vectors. So, we check both the methods and like to determine what is the answer for this problem. Then let us first method, using the first method we can express all the vectors as a linear combination of base of the three individual vectors summation C I U I and equal to 0. We consider this equation. So, this will be 2 C 1 plus 4 C 2 plus 2 C 3 is equal to 0, that is equation number 1. Then C 1 plus C 2 equal to 0, that is the equation number 2, and the third one will be 3 C 1 plus 5 C 2 plus 4 C 3 equal to 0, that is equation number 3. So, combining 1 and 2, what we will be getting is that we will be getting C 2 plus C 3 is equal to 0, as we have already done earlier, but combining 1 and 2 and 3, what we can obtain is that we will be getting C 2 plus 2 C 3 equal to 0, that is equation number 5. So, if you now combine these two equations to solve these two unknowns, from 4 and 5 we will be getting C 3, we subtract 4 from 5. So, we subtract 4 from 5, you will be getting C 3 equal to 0. If C 3 equal to 0, then from equation number 4, C 2 will be equal to 0. If C 2 equal to 0, then from equation number 2, C 1 will be equal to 0. So, in this case, in order to satisfy this equation, all the individual coefficients have to be equal to 0 individually. So, therefore, we will be getting a unique solution for this particular case. There does not exist an infinite number of solution in this case. All the individual coefficients, scalar multipliers will be equal to 0 in order to satisfy this equation. Therefore, the set constituted by U1, U2 and U3 are independent set of vectors. So, that is the conclusion of this analysis. Now, let us look into the method number 2, that is the second method by looking into the coefficient determinant. So, the determinant is constituted by these coefficients, that is by these elements 2 1 3, 4 1 5, 2 0 4, and this turns out, if you would like to simplify, 2 1 5 0 4 minus 4 1 3 0 4 minus plus 2 1 3 1 5. So, this will be 2 4 minus 0. So, it will be 2 into 4 minus 4, this will be 4 minus 0. So, it will be 4 plus 2 5 minus 3. So, it will be 8 minus 16 plus 2 into 2 4. So, it will be 12 minus 16 is equal to minus 4, and this is not equal to 0 in this particular case. So, therefore, U1, U2, U3 they are independent set of vectors. Set of independent vectors. So, from both the methods we come to the same conclusion. Okay. Now, I have another problem, example 3 maybe. We have two vectors available in R3 space. we have three vectors, we have two vectors available. u1 is equal to 3, 2, 1, u2 is equal to 2, minus 3, 0, and u3 equal to so therefore, these two are available, and we have to find out third vector in the space, so that vectors along with u1 and u2 will constitute a basis set vectors. So, u1, u2, u3 it becomes an independent, it is a basis set. Find out the third vector, so that S is a basis set. So, that we have two vectors are given, we have to find out the elements of the third vector, such that u1, u2 and u3 constitute the basis set vectors. So, if you look, so in this problem, first we do not know what is the elements of the third vector. So, therefore, we assume vector number 3, that is u3 is nothing but alpha 1, alpha 2, alpha 3, where alpha 1, alpha 2, alpha 3 are elements of this vector that we are going to determine. If that is the case, then we constitute the corresponding determinant of this problem. This will be 3, 2, 1, 2, minus 3, 0, alpha 1, alpha 2, alpha 3. Okay. So, check whether this just evaluate this determinant. If we evaluate this determinant, 3, minus 3, 0, alpha 2, alpha 3, minus 2, 2, 1, alpha 2, alpha 3, plus alpha 1. So, it will be 2, 1, minus 3, 0. So, we just keep on simplifying this. So, determinant is equal to 3 minus 3 into alpha 3. So, this becomes 3 alpha 3 minus alpha 2 into 0 minus 2, 2 into alpha 3 minus 1 into alpha 2 plus alpha 1, 2 into 0 minus 3 into 1. So, it will be minus minus plus. So, it will be 3. So, therefore, this becomes minus 9 alpha 3 minus 4 alpha 3 minus 2 alpha 2 plus 3 alpha 1. So, we will be getting 3 alpha 1, this will be minus minus plus, so plus 2 alpha 2 minus 13 alpha 3. Now, in order to get an independent set of vectors, my criteria is that for independent set of vectors, the criteria is the determinant cannot be equal to 0. So, therefore, 3 alpha 1 plus 2 alpha 2 minus 13 alpha 3 should not be equal to 0. Now, we can assume any value corresponding to alpha 1, alpha 2, alpha 3 such that this inequality is satisfied. For example, if you consider alpha 1 is equal to 1, alpha 2 is equal to 1, alpha 3 is equal to 1, you will be getting 3 plus 2 is 5, 5 minus 13, that is minus 8, minus 8 cannot be equal to is, of course, it is not equal to 0. So, therefore, 1 1 1 in along with the other two vectors u 1 3 2 1, u 2 2 minus 3 0 and u 3 as 1 1 1 constitute a basis set vectors or independent set of vectors. That means ui is basically a basis set. Similarly, one could have used any three values of alpha 1, alpha 2, alpha 3 such that this inequality is satisfied. Not necessary 1 1 1 need to be taken, one can take any other combination of alpha 1, alpha 2, alpha 3, but keeping in mind that this inequality has to be satisfied, so that that vector along with the first two vectors u 1 and u 2 will constitute a basis set of vectors. So, that indicates how will you how one can determine the dependent and independent set of vectors. Okay. Next, we move to the topic on Gram-Schmidt orthogonalization. As we have said that any fourth vector in the space can be expressed as a linear combination of the three basis set vectors in R3 space, or for that matter in any space it can be expressed as linear combination of the basis set vectors. Let us consider an R3 space which will be easy to comprehend. So, therefore, any fourth vector can be expressed as a function of as a linear combination of the basis set vectors, where u 1 to u 3 they constitute the independent vectors. And we have seen earlier in this class itself how to find out or determine the coefficients beta 1, beta 2, beta 3 if and only if these basis set vectors are mutually orthogonal to each other. Beta 1, beta 2, beta 3 can easily be determined if ui form the orthogonal basis set. The calculation will become further simplified if ui constitute a set of orthogonal orthonormal basis set. So, therefore, if you have this for I am just giving an example of 3-dimensional space. If you have n-dimensional space, then the whole thing becomes very easy. So, the coefficients, if you remember, beta n can be expressed as the inner product of y and nth vector in the space, that is the u n. So, we know this vector, we know this vector. So, this will be simply summation of y I u n I. So, the coefficient can be determined for a larger dimensional problem by simply you identify the corresponding elements of these two known vectors and multiply them and then add them up. So, this involves the simple operations like multiplication and addition. So, for a larger spaced problem, we will write a small program in computer, so that the elements of these two vectors, known vectors, will be arranged in an array, and we will identify that corresponding ith element of the two vectors will be multiplied and then being added up for all the subsequent terms, and the addition will be giving the coefficient beta n. Similarly, we will be able to, we can put it in a loop, and in only a couple of lines program you will be able to calculate all the undetermined coefficients betas in this equation. But the point is, all the independent set of vectors may not be a well behaved set of vectors. That means, basis set vectors need not to be well behaved. What do we mean by well behaved vectors? That means these vectors may not be orthogonal and at the same time orthonormal. So, for that what you have to do? You have to adopt a technique to make the basis set or independent set of vectors to be orthogonal and orthonormal. So, that technique is required, mathematical technique is required to convert the independent set of vectors into an orthogonal orthonormal set. That this particular technique is known as Gram-Schmidt orthogonalization. So, by using this technique one can convert an independent set of vectors into an orthogonal orthonormal set of vectors. So, let us next we look into the details or derivation or the technique for getting the Gram-Schmidt orthogonalization technique. So, let us look into that and see how an independent set of vectors can be converted into orthonormal set of vectors. So, for that let us consider a k dimensional space where the set H1, H2, H3 up to Hk is an independent set of vectors. It is basically we are talking about a k dimensional space. Okay. We will be getting a set from this set. These set are not orthonormal. So, we will be getting another independent set of vectors. From these vectors we will be getting E1, E2 and up to Ek set, where E1, E2, Ek are orthogonal and orthonormal both. So, let us look into the details of this method. So, we know we start with the first vector H1. So, we define E1 from this vector itself such that E1 is H1 divided by norm of H1. So, if you look into the definition of this vector E1, we can take the norm of this equation what we will be getting is that we will be getting norm of E1 is nothing but norm of H1 divided by norm of H1, and norm of H1 is nothing but a scalar. So, it comes out of this norm. So, it becomes, you just remember the properties of a norm. So, this will be nothing but norm of H1 divided by norm of H1. These two are the scalars, they will be cancelling out. So, the magnitude or norm of E1 turns out to be 1. So, therefore, this transformation ensures that the norm of vector E1 will be unity. So, we made the E1 orthonormal. Next, we consider a vector G2 such that G2 is equal to H2 minus inner product of H2 and E1 multiplied by E1. So, inner product is a scalar. So, it is basically we are formulating a vector, so which is nothing but the vector H2 minus some scalar multiplier of the vector E1, that whatever we have derived just now. So, what is the inner product of H2 and E1 physically signifies? It is nothing but a projection of H2 on E1, and it is a scalar. So, this is a scalar multiplier. So, by doing a mathematical operation on this, we will be formulating the we will be going to the next step, that will be a stepping stone for formulation of the next vector E2 of our target set, which will constitute the set of orthogonal and orthonormal basis set. So, we will proceed in the next class to complete this formulation. Thank you very much.